Hello everyone, glad to meet you here at ChinaCon. I am Li Han from Shanghai Jiao Tong University. The topic of my presentation is Distortionless MVDR beamformer for Conformal Array GNSS receiver. This is the contents of my presentation, which can be divided into the following 4 parts. GNSS is one of the most powerful infrastructures that provide positioning, navigation, and timing service for users all over the world. Similar to other existing GNSS, Beidou satellite system is also designed to withstand a certain level of radio frequency interference, which is achieved by direct sequence spread spectrum technique and is capable of coping with the most common unintentional noise in daily life. However, related researches show that a single jamming device can disable GNSS signal reception over a range of several kilometers. To address this situation and enhance the robustness of the GNSS receiver, a variety of GNSS interference mitigation countermeasures have been developed in the past decades. Among them, the spatial time adaptive processing scheme is the most powerful one. The spatial time adaptive filtering techniques utilize the antenna array combined with finite impulse response filters to adaptively rearrange the received signals at the antenna in a weighted sum version to steer the antenna array response beam pointing to the desired direction and then now pointing to the undesired interference, which allow the Beidou signals to pass and suppress the jamming effectively. Besides, nowadays the demand for conformal array is increasing. A conformal array is a kind of antenna array that conforms to its barrier surface, which is designed for better aerodynamic or hydrodynamic performance or aesthetic consideration. However, due to the non-planar curvature of the barrier surface, directional element model should be adopted, and different antenna usually have different orientation, which in turn leads to different response to the same signal on different antenna. Later, the solution for this problem will be introduced. Here, a more general conformal array model containing M elements is considered. In the global coordinate system, the position of each element is pi. For this array, first we examine the synthesis of its array response pattern. Considering that a far-field narrowband plane wave with a propagation direction of A and wavelength of lambda 0 impinges on the array, so the corresponding wave vector is k. Then we have the array response here, f, where the fc phi is the fmc phi is the radiation direction function of the m's element itself. Wm is the corresponding complex rating factor. Note that the global polar coordinate system is not consistent with local coordinate system of each element. To address this issue and for simplicity and generality, a 5-element array with a central element conforms to a cylindrical surface is used for analysis. All the elements point to the normal line and share the same radiation function. Take PR as an example to analyze its contribution to the array pattern. Here, first, θ phi is the polar coordinate corresponding to the global Cartesian coordinate system O, X, Y, Z, and phi I, Y, I is the coordinate in the polar coordinate system corresponding to the local Cartesian coordinate system OI, XI, YI, ZI of the I array element. For a signal impaging from CITFA in the global coordinate system, it first needs to be converted to a local polar coordinate of each element, which can be achieved with Euler rotation. Here, a new coordinate OI prime, XI prime, YI prime, ZI prime is defined. It is generated by translate OXYZ to make O overlaps OI. It is obvious that OI, XI, YI, ZI can be generated by rotating this coordinate system. Therefore, the relationship between the above two coordinates can be derived using Euler rotation here. Besides, the signal is assumed to be far field, so rho can be regarded as infinity. Using the definition of arctangent function, local polar coordinate can be solved as here. Now the array radiation pattern can be transformed to this. As to the element radiation function, a cosine element model is used to better depict the radiation characteristic of elements on the convex conformal surface. Based on the above analysis, a general signal receiving model for an M-element convex conformal array can be obtained. First, assume there are K interference and one Bechdel signal dt. For an arbitrary signal st with incident angle of theta phi and wave vector k, its steering vector is expressed here as a theta phi, and the array manifold of the incoming signals can be expressed as the matrix A. And for the convenience, the conformal factor matrix CFMG is defined to incorporate the conformal characteristic. Finally, the observation vector of the conformal array can be obtained as here. Through a standard step implementation of p time steps, the final step observation vector can be expressed as V, and the filter coefficients of corresponding time steps also forms a vector W. Hence, the output of the step filter is Y. As mentioned above, a Bechdel signal is expected to pass the step filter without being distorted. To achieve this object, the output signal Ys of a single Bechdel signal with steering vector CD is analyzed. Actually, we can see the frequency response HF of the step filter towards signal with steering vector CD is in the same form, and then it can be found that it is also equivalent to a FIR filter given with coefficient vector H, where HP is WP product CD. Then we can form the MVDR problem with these constraints and solve it with the Lagrange multiplier method. Now we got the optimal weights, and together with the HP, it is proved that the coefficient vector H is conjugate symmetric. Combining that P is odd, the FIR filter coefficients meet the requirement of linear phase system with a constant bias. This bias doesn't affect the positioning accuracy because it remains the same for all incoming Bechdel signals. Therefore, the proposed method is linear phased. In the simulation experiments, the array structure is the cylindrical antenna array shown before. The received signals are then converted to intermediate frequency and then sampled with proper sampling rate. The Bechdel signal SNR used in the following simulation is set to -30 decibels, and the jammer noise ratio is set to 70 decibels. The first experiment is used to demonstrate the interference separation performance of the proposed method. One beta signal and one interference impinged from 3030 and 4519 respectively. This graph shows the power spectral density of the signal received on P1 and that of the output signal. It is clear that the strong barrage jammer here is dampened to the noise floor. This is the array gain. Obviously, a fairly deep norm about minus 121 decibel is formed in the direction of the interference, while in the direction of the beta signal, there's only slight attenuation, and the SNR is improved from about minus 100 decibel to about minus 26 decibel, which can guarantee the receiver to decode correctly. Here, a comparison experiment is adopted to prove that extra consideration on the antenna direction in the proposed method can help it outperform the traditional MVDR. In the simulation, the interference direction is fixed at 4590 degrees, and the azimuth of the beta signal is fixed to 30 degrees. Suppose the elevation angle varies from 0 to 90 degrees, and the output SNR is plotted here. It can be seen that the output SNR of the traditional MVDR degrades faster than the proposed method as the altitude angle increases, where the largest deficit can be up to 4 decibels when theta approaches 90 degrees. This can be interpreted that mismatch of the signal steering vector gets larger as the elevation angle increases. Therefore, the proposed method has better estimation of the steering vector, which enables a better SNR performance compared with the traditional MVDR. Here, another comparison experiment is comparing the distortion between the proposed method and other commonly used methods, including traditional MVDR and power inversion. Here, the cross-correlation function is used to measure the distortion. All the parameters are set as the same as the first experiment, but the weight coefficients are solved in different methods, and the result with the constant bias removed is shown in this figure. Note that the ground truth curve is generated by sending the beta signal to the CCF directly. As the figure illustrated, the most commonly used method of power inversion would lead to a distortion in the cross-correlation peak, significantly undermine the symmetry in cross-correlation peak, and the traditional MVDR method would broaden the cross-correlation peak, and the above phenomena in turn result in error in code phase estimation. On the contrary, the cross-correlation peak of the proposed method is quite close to the ground truth, indicating that the desired signal is barely distorted. Here we give the conclusions. First, a convex conformal array signal processing model is proposed in this study, and based on that, a distortionless MVDR beamformer is introduced. The effectiveness of the proposed method is validated by theoretical analysis and numerical simulations. The results show that the proposed conformal array signal processing model can significantly improve the estimation of the steering vector and enhance the interference separation performance. What's more, the result also shows that the additional distortionless constraint can ensure the linearity of the step frequency response, maintain the beta signal, and furthermore, ensure the correct decoding of the standard receiver. That's all. Thank you for your listening.